All right, we are looking at section 3.9, derivatives of exponents and logarithms. All right, so to begin with, when we're talking about exponents, let's start with just the normal e to the x. The derivative of e to the x has the unique property of being its own derivative. So literally, the derivative of e to the x is just e to the x. All right, what would that mean if it wasn't just an x up here, if there was a quantity and we had to apply chain rule? All right, well then the derivative of e to the u would just be e to the u times the derivative of u. So the derivative of the outside times the derivative of the inside. Just a reminder, when we're thinking about e is not a variable. It is a number, very much like pi. It's non-repeating, non-terminating, so it's irrational. And you can see our approximation down here for e. Where we get that approximation from is actually a limit. So if we're looking for the definition or where we get that value, we understand it much more now that we've had our discussion of limits. All right, so let's say that we had e to the tangent x, and they ask us to take the derivative. So since this is not a plain x right here, we're going to need to use our u substitution. And so we're going to do e to the u times the derivative of u. So in our case, this exponent is our u. So if u is equal to tangent, then we know the derivative of tangent is secant squared. So to get our answer, then we'll just do e to the u, e to the tangent, times the derivative of u, secant squared. So e to the u, e to the tangent, times the derivative of u, secant squared. Not really any way that we can clean that up, so that would be our final answer. All right, look at the next one. For the next one, you have two distinct quantities. Here's a first one, and here's a second one. They're being multiplied, so we're going to have to use product rule. So remember product rule, we're going to do first times derivative of second plus second times derivative of first. Okay, so here's first. Now let's focus on the derivative of the second. All right, so if you took the derivative of the sine of anything, it would be the cosine of that thing. And then derivative of the inside, we would take the derivative of the 5x. So again, the derivative of sine 5x is going to be cosine 5x times the derivative of 5x. Okay, so we've got first times derivative of second, and then we need second sine 5x times the derivative of the first. Okay, so let's focus on the derivative of this first up here, e to the negative 4x. So we said the derivative of e to the u would be e to the u times the derivative of u. So e to the negative 4x is going to be e to the u. That doesn't change at all. But then we need to multiply by the derivative of u. So the derivative of negative 4x would be negative 4. So again, that's first, derivative of second plus second, and this whole piece is the derivative of the first. All right, so we could clean that up a little bit in terms of, I would put the, maybe put the 5 out in front and put the negative 4 in front here. So I could leave it that way, or because they both have an e to the negative 4x in them, I could factor out that greatest common factor of e to the negative 4x, and then that would just leave me 5 cosine 5x minus 4 sine 5x. Honestly, it's just a matter of preference. It's kind of like, would you be better off to leave your answer as x times x plus 1, or to distribute the x and leave it as x squared plus x? Either one of those is fine. It kind of depends on the setting you're in, whether you want it factored or whether you want it distributed. And that's kind of the same story here. Here it's distributed, here it's factored. Either one of those is perfectly fine with me when it comes to a test. All right, so Let's talk about derivatives of logarithmic functions. All right, the derivative of ln x is just going to be 1 over x. The derivative of ln x is just going to be 1 over x. Okay, so what if this wasn't a plain x? What if it's a quantity right here? Then we're going to apply chain rule. So the derivative of ln of a quantity, we'll call it u, is going to be 1 over u times the derivative of u. Now, something that you'll notice there, if you had 1 over u times the derivative of u, if we wrote derivative this way instead, then, let's call u g of x, okay? So if we're saying the derivative of the ln of u, where we're saying u is g of x, we would say 1 over u, g of x, times the derivative of u, the derivative of g of x. And this gives us a shortcut right here. So anytime you are taking the derivative of the natural log of a quantity, you can put the original in the bottom and put its derivative in the top. When you're taking the derivative of the natural log of a quantity, you can put the original function in the bottom and its derivative in the top, right? So let me show you what I'm talking about. We've got y is equal to ln x cubed plus 1. So obviously this is going to be my u. So if we go through and we say, okay, when we're doing ln u, that's going to be 1 over u times the derivative of u. That's 1 over u. So our quantity is x cubed plus 1 times the derivative of u. So the derivative of x cubed plus 1 would be 3x squared. So look at your shortcut. Your shortcut says, we just use chain rule to do that, but look at your shortcut. Your shortcut says put the original in the bottom. Okay, so our original was x cubed plus 1. Put that in the bottom and put its derivative in the top, and that'll be your answer. So that's a fast, easy way to go straight to that answer. It'll give you the exact same thing. All right, look at the next one. We've got the derivative of ln sine x. So this time, sine x is our u. So we're going to put our original in the bottom, and we're going to put its derivative in the top. So the derivative of sine is cosine. All right, now that could be simplified further because cosine over sine is one of our trig functions. Cosine over sine is cotangent. So we could simplify that down to be cotangent x. All right, look at the next one down here. This next one is a little bit different because it's not ln of the square root of x. It's the square root of ln x. Like if you write that, you're talking about the natural log to the 1/2. That whole natural log function is being raised to the 1/2. It's not take the natural log of something being raised to the 1/2. So I'm going to treat this just like I would anything else raised to the 1/2. Anything to the 1/2, when I take the derivative of that, it's going to be 1/2 that thing to the negative 1/2. So whatever this is in here, anything to the 1/2 is going to be 1/2 that thing to the negative 1/2. And then we're going to multiply by the derivative of that thing. So the derivative of ln x, we set up here in the very beginning, derivative of ln x would be 1 over x. So here's our chain rule, derivative of the outside times derivative of the inside. All right, and then in terms of just cleaning that up a little bit, you're welcome to leave your natural log with a rational exponent, or you can rewrite it with your radical. And as we've seen, they're not always making us rationalize our denominator, but you absolutely could. All right, so what if we want to take the derivative of a log that is not the natural log? Remember, a natural log is a base of e, log base e or ln. But if it's not a base of e, so for instance, if you look at this next one, we've got log base 10, then we have a different formula for that. It's going to be 1 over x ln a. And of course, if this is not a plain x, if it's a quantity like we're going to see here in just a second, we're going to use chain rule. So you could think of this as a u, so that would be 1 over u ln a times the derivative of u. All right, so let's go ahead and look at this one. If this is going to be our u, and you can see that our base is going to be our a, so we could come over here and we could say, okay, that's going to be 1 over u ln a. So for us, our u was 2 plus sine x, and our a was 10. So 1 over u ln a. All right, then to finish off our chain rule, we need to multiply by the derivative of u, right? So the derivative of 2 plus sine, derivative of 2 is 0, and derivative of sine is cosine. So we could put that cosine in the numerator, and then down here in the bottom, if you want to distribute the natural log of 10, you can, or you can leave it as it is. All right, then let's look at an exponential. We've already done the derivative of a natural exponential. That's a base of e. But what if it's not a base of e? All right, so again, you can see here I've got an exponential with a base 10. So you can see the formula that we're going to use here. And again, applying chain rule, if this is not a plane x, as it's not for us in our problem, then we would apply chain rule and say a to the u ln a times the derivative of u. All right, so for us, you can see that a is 10 and u is x squared. So if we apply that, we're going to have a to the 10 to the x squared, because a is 10, 10 to the x squared, and then again put that 10 in for a, and then we need to multiply by the derivative of u to finish off our chain rule. So again, following our formula, that's a to the u ln a times the derivative of u. Now, notice that you can't combine this 10 and this 2 and make it 20 because this 10 is being raised to an exponent and this 2 is not. So we need to leave those separate. All right, the last thing we want to look at is something called logarithmic differentiation. And in order to do that, we need to review for just a second the properties of logarithms, all right? So remember that when you have a log where your bases are the same, you have two logs that are being added, you can multiply them, or the reverse is true. If you have the log of something being multiplied, you can break that into two separate pieces that are being added. Similarly, with division, we subtract, and when you have an exponent, it can be moved out in front and made a coefficient. So when we get to this next problem, if you'll notice in original green here is our original problem. If we try to take the derivative of this, it's going to be a nightmare. We've got a product, we've got a quotient. The problem is all the multiplication and division. Okay, well, if we insert an ln on both sides, that's a legal move. What you do to one side, you do to the other. Now I can go through and take my derivative, and look how much easier this is going to be. Because over here, if you have two things that are being multiplied, you can break them into two separate logs that are being added. And if you have two things that are being divided, you can break them into separate logs that are being subtracted. And those exponents can come out in front to be our leading coefficient. This was 2 the 1/2 because it was a square root. So that's where our 1/2 is coming from. And then our exponent of 5. Now I don't have to do a product or a quotient or anything else. I can just do my normal implicit differentiation. So remember implicit differentiation from our previous section. We're going to go through and take the derivative in terms of x. So the derivative of ln y is going to be 1 over y, and since that's not in terms of x, we have to leave a dy dx. Over here, we've got our 3/4 derivative of ln x is 1 over x. We've got our 1/2 ln, so remember we're going to put the original in the bottom and its derivative in the top. And then same story here, we're going to put its original in the bottom and its derivative in the top. Now we just need to get dy dx by itself. So to do that, I'm going to multiply both sides by y and then do a little bit of cleaning up. But here's my problem. That's supposed to be the derivative of y in terms of x. So the very last thing I want to do is I want to replace y with what it was equal to. In the original problem up here, y was equal to this guy right here. So all I have to do is replace y with that original function. and then here was the other piece that I had, and that would be the derivative of y in terms of